Hello, everyone. Today I'm going to be giving a talk called Inside the Black Box, How Does a Neural Network Understand Names? My name is Blair. I'm a senior research engineer at Basis Technology, whose flagship Rosette platform provides a variety of text analytics solutions in a multilingual setting for companies, ranging from information extraction and document enrichment to identity matching and resolution, and multilingual search enhancement for platforms such as Lucene, Solar, and so forth. So, briefly, here's what we're going to cover today. We're going to start with a brief introduction to what the problem of named entity recognition is. We're going to briefly compare and contrast between traditional machine learning and new deep learning approaches to machine learning in the context of natural language processing. We're going to look at some specific architectures used for named entity recognition, and then we're going to cap off with trying to see what these models are actually learning about data. So named entity recognition is an important problem in natural language processing, or NLP, where you're trying to develop a system which can automatically detect the names of people, organizations, and locations in text, and many more types as well. And this can be related to search in a number of ways, such as you might extract the entities inside of a document and use that to enrich the information that you're capturing about different individuals across your data, and things like that. So here's an example of this in action. We see that the system has detected that Elon Musk is a person, Mars is a location, and next year is a date. Now, especially in English, when you glance at an example like this, you might think, well, this is not a very hard problem, right? Elon Musk and Mars have very clear morphological features that indicate the presence of an entity in a document, namely capitalization. I mean, next year might give you a hard time, but you get the idea. But the challenge, so you could go ahead and write out some rule-based approach to detecting where these entities are, but the problem that you're going to run into is properly tagging the types of these entities. Because in this instance, if you just look at the word Mars, here you can clearly see it's a location, but in general, the word Mars can refer to both a location or a brand of candy bar. And you want to find a system which can properly handle both. So the key here is that context is important. And this is an optical illusion some of you might have seen before, just to kind of illustrate this point. When you look at this image, your brain clearly sees that B is a lighter shade of gray than A, but if you remove the surrounding contextual information, you see that they're in fact the same color. So how does this actually manifest itself in the context of named entity recognition? Here's an example where it says Camp Place, Spain. 9 times out of 10, probably more than that, if you see the word Spain, you're going to think it's a country, but in this instance, it's actually a song. Here's another more straightforward example. When you see the word mom here, you as a human reading this sentence can clearly tease apart the fact that mom is not referring to a person, but is instead referring to a television show. Now, if you were to just train a statistical model to try and decide these instances, almost all of the data that you would be feeding into it would have mom be a person. And so you need to develop a system which can actually handle this 1% of times where the context informs the type of entity that you're going to be tagging this as. Okay, so first, let's talk about how we can actually formulate this as something we can write an algorithm to do. And the way we do that is we write it as what's called a sequence labeling problem. So what your system is going to do is it's going to look at every word in your document and assign a label to it. So if a word is not part of any type of named entity, which most will not be, we're going to give that what's called an O label, which stands for outside. Similarly, you're going to have instances where, in this example, you see basis and technology are organization. Those are part of an organization entity in your document, and so we want the system to tag them as such. But you run into an issue where if you were to just tag these as simply organization, it would be ambiguous as to whether basis and technology were 2 independent organization entities or if they were a 2-word single entity. And so that's where this B and I business comes in. And so what we're going to do is we're going to tag the first word in the entity with B organization, and all of the subsequent ones as I organization. And then when you're reading this sequence and interpreting it, you're going to then collapse these into a single entity, and that's what this dotted line is showing. All right, so in an enterprise-grade system, you're going to have a variety of systems feeding into this decision-making process of what labels you're going to be assigning each word. You might have a dictionary-based system, which is computed from some data set you have lying around of known entities. You might have a rule-based engine, which could incorporate domain-specific information about your data set or some specific linguistic features you want to account for. Or you might have an AI-based engine, which is just going to use statistical properties of your text to assign different labels to words. Now, as this is an AI session, we are going to be focusing on the last of these for the remainder of this talk. And before we get into the details, I just want to briefly compare and contrast. This slide got messed up. That's very sad. Briefly compare and contrast the traditional approach to doing machine learning versus newer deep learning approaches in the context of NLP. So for illustration purposes, this slide shows a sentiment model, not an NER model. And so the task here is you're going to be given a piece of text, and you want to just simply classify it as either positive, negative, or neutral. So I Love This Movie is clearly a positive piece of text. So in a traditional machine learning environment, you're going to first take your text and run it through some feature extraction pipeline. Now, these features are going to be something that people have sat down and handwritten out to incorporate specific properties of that text, such as the words in it, the parts of speech in it, whatever. Those feature values are then going to be run through some vectorization process, which will then convert them into some numeric representation where you have a vector of where each dimension corresponds to some well-defined property of the text. This vector is then fed into some sort of classification algorithm, such as a support vector machine, and that will give you your result. In contrast, in a deep learning environment, you're going to start with your text, and instead of running it through handcrafted features, you're going to rewrite it using these things called word embeddings, which I will be going into on the next slide. But the basic idea is that these are pre-trained vector representations of the words in that language, and they capture the semantic information of those words. And the key word there is that they're pre-trained. You can use these. You can come up with these embeddings once, and you can reuse them for a variety of different NLP tasks without any further feature engineering specific for that task. Once you have your input rewritten using those, it's fed into a deep model, which can have a variety of different shapes or architectures, which capture different relationships between different parts of your data. Now, from an engineering standpoint, the key difference between these two is that in a traditional environment, once you've settled upon a good classification algorithm for the task that you're doing, most of your engineering time will be spent on this feature extraction step, coming up with new features which better capture the nuances between the different classes of your data. In contrast, in the deep approach, because you're just using these pre-trained representations all the time, most of your engineering is spent instead developing new model architectures that capture different patterns between different parts of your data that help it learn to tease your different classes apart. So like I said, I was going to briefly describe these word embedding things. So once again, you are simply assigning a vector to each word in your language, which somehow represents the semantics of that word. And you can do interesting linear algebraic operations on this vector space, such as in the paper that largely popularized their use today, they have this example of an analogy task. And so what we've done here is we've taken the representation for the word Tokyo and subtracted it from Japan, and you can take that difference vector and then add it to Berlin, and that will put you right around the vectors for Germany, German, European, Europe, and Africa, which is pretty cool. You can do this. You can just negotiate this semantic space using simple linear algebraic operations. And at some level, that's really all these deep models are doing. I mean, if you want to talk about the classification example of sentiment, it's just like Yoshua mentioned this morning of you're essentially just transforming the semantic space into something that's separable into the different classes that you're trying to tease apart, positive, negative, and neutral. So, how do we actually apply this to named entity recognition? Like, how would you approach a deep named entity recognition model? So if anyone has taken a course on neural networks, the first thing that you learn is about these feedforward neural networks, which, glossing over some details, you're effectively just doing a couple of matrix transformations with this network. And so what you can do is we can take the word that we're interested in tagging, so in this case, Spain, and we can take a context of a window of a fixed size around that word. We show 2 words here. And you can take the vector representations for all of those and just feed that into this feedforward neural network. This will transform it a couple of times until you eventually end up with a probability distribution of potential labels for the word Spain. And so if you're going to have, say, 3 types of entities you're interested in, person, location, and organization, you're going to end up with 7 outputs here, representing the probabilities of both the I and the B tags for each of those types and the probability of the O tag for that word. Now, this works well enough in this case, but again, notice that in this instance, Spain is not a location. And the reason we know that is because it's preceded by the words listen and to. Now, while those happen to fall inside our fixed window size in this instance, we don't know that's going to be the case in general. And so what we would like is a network that can more flexibly incorporate context from other parts of the document into its decision-making process that might come from further away. So what we're going to do is we're going to instead change to what's called a recurrent neural network, or an RNN. And so I've simplified the previous model. I've gotten rid of the second layer, and now we're only feeding in the representation of the current word. That's great, except we have no context. We're back to this problem that we had with Mars, where we need to incorporate this information. And so the trick is we're actually going to take this middle layer 1, and as we go along each word of this document, or each what you would call time step of this document, we're actually going to feed in that layer back into itself as an additional input as we go through. And so essentially this is going to accumulate as we're scanning through the document, go in with the current word's representation, and both be used to predict the probability distribution for that word. And so this is a more mathematical representation for what's going on, but the key intuition is that this network is actually able to remember information as it reads through a document. Now this feeding back into itself might look a little confusing, so this is kind of a more intuitive picture of what's going on. You're feeding in the current word and the previous time steps output in order to get your end prediction. Now this is great, except you have another problem, which is consider a really long document. And you have this listen to Spain at the beginning, and you use this listen to context information to come up with the label for Spain. And that information is stored inside of this fixed size layer 1 that we've reorganized. If you have a very long document, where at the end you just have some guy named John, say, then you still are holding on to that information that you used at the beginning in order to determine the label for Spain. And you don't have the room to incorporate the context that you would need for later predictions because you just run out of space, essentially. And so what you really want is some way for this recurrent network to actually be able to forget about information it no longer requires for doing further predictions. And so that's where this notion of a long short-term memory cell comes in, or an LSTM. And glossing over the mathematics of it, essentially it's just the same thing as before, except you're adding an explicit forget mechanism to this cell. So what does our network look like now? You can see that we're threading along this information through our LSTM and coming up with these label predictions. But if you look at this example closely, you see something interesting. When you read this, Washington said in Chicago, you as a human can tell that Washington is referring to a person here because it is the word after it is the word said. But the network, because we're threading through the context from left to right, actually at the time that it's producing this probability distribution for the word Washington, does not know about the word said. And 9 times out of 10, unless you're trained on some US history corpus maybe, Washington is going to be referring to a location, either the state or the city. And so we still have this problem of missing context. So what you do to account for this problem is we're going to take this LSTM layer, we're going to copy it and flip it around so that it scans from right to left, and then combine both LSTM outputs into a single contextualized representation for that word. And so you have two separate flows going on here which capture this context. And this basic LSTM, what we call bidirectional LSTM or bi-LSTM structure can be replicated to capture more interesting patterns across different distances of your data. You can do it twice, you can do it 3 times, as many times as you like. But the trade-off that you have when you do this is, aside from the fact that it's just going to be slower because you're doing strictly more operations, and while LSTMs aren't awfully slow, they certainly aren't cheap. You have a more practical problem of you're adding a lot more parameters to this network, and so it becomes much more prone to overfitting your data set and generalizing much worse in the wild. And so in practice, you're going to really limit this to maybe 1 or 2 layers of bi-LSTMs in order to get a decent approximation for most sequence labeling tasks in natural language processing. Okay, so now another thing you might have noticed, if you think about how we defined this labeling mechanism that we're assigning to each of these words, the I version of labels needs to follow a B version of that label, right? Because if you have the I tags only exist to disambiguate between adjacent entities. Now, while just using a plain bi-LSTM will likely follow this constraint most of the time, you don't have any guarantee that that will be the case, and you could get some bogus output from the network. And so this step of converting probability distributions into labels, called decoding, instead of doing it independently for every word, we can instead use this thing called the conditional random field, or CRF, in order to do a global prediction of the most likely sequence of tags. And so this sounds like a change in wording more than a change in any semantics, but the effect of it is you end up minimizing the probability of any nonsensical sequences of labels appearing in your output. And so the last piece that we're going to add to this network is, like I mentioned at the beginning of the talk, English has a lot of rich morphological information in words, such as capitalization, which will help this named entity recognition task. But word embeddings, while they capture the semantic meanings of words, they don't necessarily capture this same morphological information. So what we want is we want to add some component of the network which does. And so what we can do is take this bidirectional LSTM structure and shrink it down so that instead of operating on every word in your document, it's going to operate on every character in your word. And you're going to do this for every word. We've only shown it for the word said, but you can imagine this is happening for everyone. And you combine that with your pre-trained word representation in order to get a more morphologically sophisticated word representation that you can feed into this LSTM. Now, you can actually get tangible improvements in performance when you do this. So these are F1 scores measured on an internal evaluation set we've collected. And you can see that when we add the character level encoding to this network, our English and Arabic accuracy, or F1, excuse me, bumps about 2 points. And Korean goes up by almost 4 points. So you do get a lot of advantage from adding this morphological information to the network. But we've been kind of down in the deep technical level, and so kind of coming back up for air, the basic structure that we've presented here is you're taking your input, running it through some character encoding step, then running it through some word encoding step, and then decoding the result into some sequence of labels, okay? Now, our choice of using a bidirectional LSTM is a choice. There are plenty of other possibilities that you can use, plenty of other architectures you can use for each of these steps, and you can actually even forego the character encoding step if you so choose. And so what we've provided here is kind of a direct copy of what's in Lampel et al. 2016. But Shen et al. 2018 gives this big table of different reported combinations, and you can actually extend beyond this to your own experimentation. So, before we close out, what I would like to talk about is what does this LSTM actually learn? So one of the big criticisms of, or you could say criticisms of deep neural networks is that while with a traditional network, or traditional machine learning algorithm, excuse me, you have these well-defined input features, and therefore you can look at the weights of those features and come up with some reasoning as to why your model came up with a certain decision. Because the representations that we use in these deep neural networks are learned instead of handwritten, you end up with this explainability issue where you don't know why your network is making certain decisions and why it's tagging certain things a certain way. And what we would like to do is try and peek inside this black box and figure out what's going on and what the network is actually learning. And so what we did is we did a little bit of analysis. If we look at this bidirectional LSTM network, let's zoom in on this first forward LSTM cell. And remember, this is threading along information as you go through. And that information is a series of neurons that we're going to look and see how it evolves over time. So we wrote a tool which does this. And you can see there's some input up at the top. And there's a column for every word in that input, and each row corresponds to a different neuron that's being passed along over time. And so what we wanted to do is feed in a variety of different inputs and look for interesting patterns in the activations of these neurons. And we found a couple. For example, neuron 280 seems to get positive around some punctuation marks. Now, the exact reasoning for why that's relevant to the task of named entity recognition is not totally clear necessarily. Could be for, say, a situation where you have like New York, comma, New York. But the moral is that you see that our network has actually learned that there is some statistically significant advantage to being able to detect these regions of text. Similarly, if you look at neuron 189, you get a much more interpretable behavior of it seems to get very negative around potential locations. So if you look at the first and the third example here, you see that whenever it sees the word in, the activation drops significantly and it continues to stay negative for the remainder of the location that follows in. But more interestingly, you see in this middle example that it sees the word in, drops, goes through the word van and I, and then once it's realized that this potential location is over in the text, the participle phrase or prepositional phrase is over, then the neuron activation reverts to a more neutral state. And so, again, this is one of many factors that the model has teased apart in the training process as important for determining where these named entities lie. So, in summary, I gave a brief description of what named entity recognition is, and so deep neural networks allow us to leverage nuanced features in text without having to handwrite features in a laborious way. Accuracy scores in these models increase noticeably when you incorporate character level information. And if you do some creative analysis on the activations of this network, then you are able to kind of get a better idea of what goes on inside that black box. So I know that was a bit of a short talk, but thank you. Any questions?
I have a question.
Yes.
Those character embeddings.
Yes.
Did you use any technique like, I don't know, Facebook fast text or anything to embed each character?
That's an excellent question. So the question was whether we used anything like Facebook's fast text for character level embeddings. And for this experiment, we did not. What we ended up doing is we used pre-trained word level representations, and then for the character level ones, we randomly initialized them, and they were trained during training of the NER task. So the intuition there is for training word embeddings, you need a massive amount of word data, word examples, but for character level information, you have sufficiently enough data on a reasonably sized data set that you have enough examples to train these character level embeddings just for that task, as opposed to using a pre-trained set.
Did you come up with this idea by yourself, or you read something in the papers or any research that character engrams would improve the
So
bios?
this was the work that was done by Lampel et al. 2016.
Okay.
Yes, I would refer you to that work for that. Yeah. In the back.
What dimension was the character embedding?
Excellent question. The question was, what dimension is the character embedding? I want to say it was 150 is what we used. It was that or 300. I think it was 150 for the character embeddings, though. All right. Anyone else? No? Okay. All right. Well, thank you very much.